remove one electron, you will have gas ion helium with only one electron. So basically, the electronic configuration of this gas ion will be similar to the hydrogen. So now we move to the system when you have more than one electron. We call many electron atom. So in the system of hydrogen, you understand that when you take different orbital, 1s, 2s, 2p, 3s, 3p, 3d, you understand that they are split into different energy level, but in the same sub-layer, the orbital 2s and orbital 2p have the identical energy level. Of course, they have higher energy than 1s, but 2s, 2p have similar energy level. And 3s, 3p, 3d have identical energy. However, when we move from hydrogen with one electron to other atom where you have more than one electron, the energy of an orbital will be not identical, as in the case of hydrogen, but the energy of an orbital increase with the increasing value of L. Let's say if you have 2s, you compare with 2p, the orbital 2p will have a higher energy. In the same chance, 3d will have a higher energy than 3p, and 3p higher energy than 3s. So here we can summarize a little bit the energy diagram for the hydrogen orbital with one hydrogen atom with one electron or other one electron ion, and the same energy diagram, but now you see the splitting of the orbital 3s, 3p, 2s, 2p for the system of many electrons. You see that lowest one will be 1s, and then go to 2s, 2p, 3s, 3p, 4s, 3d, and 4p. Okay, and then you can notice that the 3d orbital have higher energy than the 4s for the moment. So we're back with a little bit more physics. Let's say in the last lecture, you learned already about 3 quantum numbers: N, main quantum number, angular quantum number, and so you have N, L, and ML. So now we talk about, because electron have a charge. So when a charge moves in the space, it can behave like a magnet. So some people can say that, okay, you imagine you have a electron, we can rotate. If you have rotate, the rotation is the same direction of the clock, so the clockwise rotation, you have one magnetic field create. And if you have the second rotation in the inverse direction, you will create also the magnetic field with the inverse direction. So by understanding that, people say, okay, because the electron can move in 2 directions, so it will create the magnetic field with 2 different directions. So we can imagine that the electron have 2 spin, 2 movement direction. We can say electron can create the magnetic field when it's moved by the upside or downside. It's something quite easy to understand. It's easy to imagine, but actually we have to remember that this imagination is quite, how to say, artificial, too simple, because we mentioned in the atomic structure discussion that the electron is point-like particle and there's no dimension. So you cannot imagine something with no dimension move like a big particle. So the reality is basically in the quantum mechanics, you have a fourth quantum number, which is spin, and by mathematical point of view, this spin have only two values, minus half and positive half. So now if you want to put the electron with different spin in one orbital, you follow the Pauli exclusion principle. The principle stated by Pauli say that no two electrons in one atom, in an atom, can have the same set of four quantum numbers, N, L, ML, and MS. So let's say maximum two electrons in one atom can have three identical quantum number, but the fourth one should be different. So in one orbital defined by a given set of three quantum number N, L, and ML, it can hold only a maximum of two electrons with two different values of spin, minus half and positive half. So it say that in one atomic orbital, you cannot have more than two electrons. You can have 0, you can have 1, or maximum 2, but not 3. Okay. So now, what we can learn from this? It's quite easy to understand. If you remember well, the chemistry at the grade 10 at high school, there are no difficulty to understand about the electronic configuration and about the fact that electron have two spin, minus half and positive half. Now, you may want to ask question, what could be the significance of this? How can we apply the fact that in one orbital, you have maximum two electrons, and when you have two electrons, they should have two opposite spin, minus half and positive half. You understand, in terms of energy point of view, two electrons in one orbital should have identical energy, right? Because the energy is defined by the orbital, not by the electron, by the orbital, and it's defined by the set of three quantum number, N, L, ML. But then when you spin two electrons in this orbital, you will have the same energy level. So it say you cannot distinguish which electron and which electron. The two electrons are identical, so you cannot say which one is upside, which one is downside. So let's say you have two electrons, like this. Okay, so they are at same energy level. You cannot distinguish at the ground state, at the normal state. Now, what you can do? You apply an external field. Okay, when you apply a field external like this, so what will happen? The electron, this one, who aligns in the same direction with the external magnetic field, it will have low energy level. And then the one who is in the opposite direction with the external field is going to have higher energy level. So let's say you start from a system with identical energy. When you apply external field, it will split it into two populations, one at the lower energy, arranged in the same direction with external field, and the other population at the higher energy, which are arranged in the opposite direction of the external field. So now you can distinguish the two populations. So if you want to see the signal of this one, what you can do, because now it's split into two energy levels. So if you apply another energy, enough to make this electron from here jump up to this level, and then you stop it, it will be back. So you can record the signal of this electron transition, electron movement. So now you can say in the same direction with external field, do you have any electron in this orbital? And in the opposite direction of the external field, do you have any electron? Okay, so basically you can take a photo. You can distinguish the electron which has positive half spin or negative half spin. If you don't apply anything, then you cannot distinguish these two electrons if they have, because they are in the same energy level. So what experimentally we can do? You have here two electrons. Okay, so when you apply the external magnetic field B, you have the potential of electron in function of the external field you apply. So you can see that the higher external field you have, the energy level will increase. So let's say if you increase the value of B, it will increase the splitting of electron. Then when you have the splitting already, you send another, we call the radio frequency radiation. You can excite one electron from here up, and then when the radio frequency radiation stops, you will see the electron be back. So when it's moved up, you will see the absorption, and when it's fallen down, you will see the emission. So you can record the absorption signature, and you see whether you have an electron in the ground state in this case. Can you understand what I mean? Are you listening my lecture or not?
Yes.
So basically, now you are 200 students in this class. If Professor Đinh Thị Mai Thanh or Professor Jean-Marc Lavet say that, I have 10 scholarships for excellent students. I want to award for 10 students among 200 students in your class. Who should I award? To whom should I award this scholarship of excellence? How can I do? I need to, you are in the same class, right? So basically, for the moment, you are at the same energy level. You are at the same level. So I cannot say that, okay, you award this excellent scholarship to Mr. X, Mr. Y, or Mr. A or Miss B. I cannot do like that, okay? So what I can do? I can propose you guys one examination. So when I apply an examination, I say that if you have the score of more than 10, you will pass my examination, and you are in the group who can receive the scholarship. So after the first test, with the difficulty quite low, I mean the test is quite easy, you will have two groups. One group of 100 guys who have more than 10 at the score, and one group of 100 guys who will have less than 10. So I can say that, okay, now in this group, you have 100 guys have higher level up based on the examination, higher level, and 100 guys at a lower level. So if Professor awards a scholarship, he will choose the 10 or more 100 guys. Imagine now, if I increase the difficulty of the test, then the group, you will have the higher splitting. The group of excellent guys who can pass the test will decrease in the number. I have only 50 guys who can pass the test and 150 guys who will fail. If I increase further the difficulty of the test at the level of the national Olympiad competition, then probably only 10 guys who can pass the test and less and 190 guys will fail. So in that case, I know exactly who I can recommend to Professor Jean-Marc Lavet or Professor Đinh Thị Mai Thanh to award the scholarship of excellence. So the same thing here. If you have two electrons in one orbital, they are in the same energy level, like you guys in the same class of general chemistry. I cannot say which one is more active, which one is less active. Okay, so how I can do? I apply an external magnetic field. The magnetic field has one direction. In the orbital, you have two electrons with two opposite directions. So the one in the same direction of the external magnetic field will have a lower energy. And the one go opposite of the external magnetic field I apply will have a higher energy. When I increase the field I apply, the difference energy level between the opposite guy and the same direction will speed further and further. Okay, so now I know that there are one guy at higher energy and one guy at a lower energy. So if I apply external field to excite, to kick the one at the lower energy to go up, then I can see the signature. I can see how it absorbs the energy I set. So when it absorbs, I say that yes, there's one electron at the lower energy. Now it's excite to be up. So I know that there are one electron in the lower energy in the spin. It quick is the same direction with the spin I apply. Is it correct? If I do not see any signal, when I send the signal from external radio frequency from the external, I do not see any absorption. That means that no electron can absorb the energy I send. So that means there's no electron which have the same direction with the external magnetic field I apply. So it means there's zero electron in this orbital. Can you understand?
Yes, Professor.
Okay, thank you. So for example, take the case of what we are doing in the lab. So here you see my slide. Okay. So in our lab, we work on this cluster. Okay. So when you see this, you can understand this cluster equal to MO4. 3 times S2 minus 2, 6 times S2 minus, like this. So let's say here you have a total negative charge of 12 minus 2, and you have 4 which is 12. So in total you have net negative charge of 2, right? And you see later that this molybdenum has MO. The MO is D6. So if I have MO4, so I will have D4. Okay. And if I have MO5, I will have D1. Okay. So in the case I have one molybdenum 4 become molybdenum 5. So how I can keep the same two negative charge? Because one positive charge increase, so it's very likely that here you have S2 minus, you get one more electron to become radical like this. So you can imagine like this one, in terms of formula, it become -3. So you will have the same net charge here. Okay. So here you have a 2 negative, and here you have one single electron. So it look like D1 as well. Okay. So now you have orbital D, you have one single electron. How you can detect, how you can recognize this electron? You apply external field, as I mentioned. So you will have an energy splitting like this. So the electron will be here because in the same direction with the external field. So after you speed like this, you apply energy from radio frequency. It will excite here, and this absorption will give you this kind of signal and this signal. Okay, so you can know here you have one electron radical like this one, and here you have MO pi iron. If I don't apply this kind of spectrum, I would think that my cluster have only molybdenum 4, and all the sulfur here is either S2 minus or S2 minus. But when I put in the spectrum, when I put in this EPR represent for the electron. ERP is electron resonance. Paramagnetic. Okay. So later you will have a concept of paramagnetic. That means it responds with external magnetic field you apply, or diamagnetic. That means it will not respond anything. So in the same thing, if you ask question whether inside the cluster you will have a molybdenum 6. But molybdenum 6 means D0. D0, that means here you have a 0 electron D. So of course here you will have a 0 electron. That means when you send energy, external energy, there is nothing will be able to absorb. So you will have a signal like this. There is no absorption. So by this kind of advanced technique, you can identify the D1 species, for example, the molybdenum, or the radical like the sulfur very efficiently, while by the other technique it's quite difficult to recognize. And you will see that in one component, it's not always what you imagine, molybdenum 4 and sulfur 2 minus or 2 or 1 minus, but sometimes you have a radical. And this one has 2 minus, and with radical is look like this one, 2 minus, and you add one more electron. So later by the bonding theory, you understand that here with single bond you have a 2 electron, and you have a 1 more electron equal to 3 electrons. So here you have a kind of system with a 3 electron in the bonding. So I hope that I can illustrate, I can demonstrate to you that by understand the spin of electron in one orbital, you can apply it to understand your chemical compound, your material, and the behavior of the material and the chemical compound, thanks to the spectroscopy, advanced spectroscopy called electron resonance paramagnetic spectroscopy. Okay, it's not like you understand you learn the you learn the two spin number of the electron for fun and for to be forget later. No, they people describe the spin number of electron because after that there's important application in the science. That's what my main message to you guys. Okay. Any difficulty to understand here?
No, Professor.
Okay, thank you. Okay. Oof. What it is. Let's we move on. Okay. So as we mentioned, the spin, the electron have two spin number, minus half and positive half. And in one orbital, we will have only maximum, two electrons with the opposite spin number. So now, how we can express, how we can draw orbital? So basically, a convenient scheme for orbital and electron to be described. So you describe one orbital by one box and one electron by a row representing the spin half or minus half, up or down. So let's say here you have one box representing one orbital, and one electron is one row. When it's up, it means the spin number half. And here you have the second spin number, which is minus half. Okay? It's not difficult to understand. So, about the terminology of electron configuration. By definition, electron configuration is the way in which the electrons are distributed among the various orbitals of an atom. When we talk about the electron configuration, without further comment, we should understand that we are talking about the fundamental electron configuration. That means the most stable one. And the most stable electron configuration of one atom is the ground state, or the lowest possible energy state of this atom. Okay? So the orbitals are filled in order of increasing energy. Because when I mentioned in introduction and then in the energy conversion lecture, that in the nature, all the system try to occupy the lowest potential energy to get most stable state. Low energy, you are more stable. When you increase the potential energy, you have a tendency to fall down, so you are less stable. So the ground state is the lowest possible energy state. So when you start to fill the electron in different orbitals, because the different orbitals are arranged in different energy level, so you start from the lowest energy orbital and then you jump up. Okay. So for here, to give you an example of electron configuration, so we talk about lithium. Why I take the lithium as an example? Because a lot of people are talking about the lithium battery, which could be the future energy storage technology. With VinFast already released the first electrical car where they use lithium battery. So if you take lithium battery, you know that it has 3 electrons. So what could be the electron configuration of the lithium? You have one orbital 2s, 1s, where you have 2 electrons in the opposite direction because they have 2 different spin number. And then the third one should be in the orbital 2s. So in the format, we say that lithium electron configuration is 1s2, 2s1. So that means in the orbital 1s, you have 2 electrons, and in orbital 2s, you have 1 electron. So what about nitrogen? So nitrogen have 7 electrons. So you start, by the rule, you start from the lowest energy level orbital, so it's 1s. Then you go to the 2s and you go to 2p. So in the orbital 2p, you have a px, py, pz. They are different in the direction in the in the space, but they have identical energy. So you don't distinguish in terms of energy px, py, pz. So now you take 1s first. You fill with 2 electrons. So here you fill 2 electrons for 1s, and then you fill 2 electrons for 2s. You cannot fill more because by the equation rules. So you have already used 4. It remains 3 electrons. Whether you fill by 2 electron here, 1 electron here, and then empty here. Or you will say 3 electron, X electron will occupy 1 orbital. So basically, the nature, as I mentioned, the nature, the key of the thing is energy. The system will adopt the electron configuration which have lowest energy level. So when you have 1 electron already here, you put another electron because they are both negative charge. So they are not attract each other, but they repulse each other. They try to repulse each other. So if you want, to force them to be in the same orbital, you need to pay energy at least at the same amount of energy equal to the repulsion energy of the 2 electrons. So that means you need to pay more energy. So in that case, you would prefer to put X electron in 1 orbital, single one in single orbital. So you do not need to put more electron to force the 2 electrons get in 1 orbital. Okay. So by the law of the energy optimization, the ideal electron configuration will be this one, where X electron occupy 1 orbital. So here, sorry. So here, summarize how you can see the electron configuration change when you go from lithium to barium, boron, carbon, nitrogen. And if you go to the number 8, which is the oxygen number 8, so that means you need to put 1 more electron here. If you go to the fluoride number 9, so it have 1 more electron here. So you have a Leon, so you have the next electron here. So you see that when you have 1 more electron, you will try to finish in orbital by remembering, keep in the, remember, important keyword is energy. You do whatever you want, but need to have the lowest energy level. Okay, so how we can, and we can see we already know how to write the electron configuration. So the normal one we write like this for the sodium with 11 electrons. So it's take space and it take time. So they propose to use the condensed writing. So what is the condensed writing? So you see that the sodium, which have 11 electrons, and if you compare with the Leon, with the inert gas with 10 electrons, you will see that the differences is only this one. So you can say, you can write the sodium like the configuration of the inert gas that's before this element, and US the electron makes the difference between this element and the electron configuration of the inert gas before it. So use the node per electron configuration to shorten the other element electron configuration. Okay, when you want to write the condensed writing electron configuration of 1 atom, you look what could be the closest node per gas element of this atom, and you use this node gas electron configuration as a reference. You add up the number of electron difference between the node per gas and the element you are considering. Now, to ask question how to build electron configuration of 1 atom with several electrons. So here is a Git instruction. How you can do it? You start from the orbital 1s, this one. So when you have electron, you invert 1s, and then 2s, and then 2b, like this, by this direction. So that means it will fin 4s before you fin 3d. Okay, for the moment, it's like that. So remember, 3s will have a lower energy than 3d. So the 3s, 4s is fin before the 3d. The same for 5s, 4d, and 4f. But you will have some exception. In the chemistry, I'm so sorry to say that, you will have a lot of exceptions. So for example, the case of copper, if you fin by using this diagram, you will have this electron configuration because it will fin 4s before 3d. But in reality, people use this electron configuration. Okay. And for the chromium, normally if you use this diagram, it won't come out with this electron configuration. But if you pick up the periodic table of elements, you will see that they show you this electron configuration. Anyone can explain why this difference, why this exception? What could be the reason behind this phenomenon, where you see that the 4s become having higher energy than 3d? So the 3d should be fin first before 4s. Anyone can comment?
Yes, may I?
Yeah, please.
Okay, so I remember in high school, my teacher told me that each elements want to reach their full electron field state, but copper and chrome, they need a lot of electron to get to their noble phase. But if they so they can't reach to their fieldless phase, but they can reach their half field phase just by relocating one electron from the d orbital to the 4s orbital.
Yes, thank you. It's correct. Basically, when you have a d orbital and you have a possibility to have all the d orbital fin of the electron with a pair of electrons, that means all pair orbital d, like d10, it could be excellent. So the atom prefer to have d10. In the second preference, if you can have d5, that means all the 5 orbital have a half fin with a single electron, then it could be favorable. So that means when you have a d5 or the d10 possibility, the d element will prefer to have this electron configuration. Okay, so that's the main the first main observation to explain the exception. And the second thing we need to consider here also that we are talking about the 1s, 2s, 3s, 4s, and so on. In this alignment of energy level is correct when the orbitals are empty or when the orbitals are filled with the limit number of electrons. When take into account the case of 4s and 3d. Okay, so from here, you can see that the 4s will have a lower energy level than 3d. Okay, it's correct when the orbital 3d is empty. Okay, but when the orbital 3d start to fill electron, because you have 5 orbital d, 5 AOD. So you can maximum 10 electrons in this orbital d. When the orbital 3d start to be filled by electron, more electron you add into the 3d, the energy level of the orbital 3d low down. So if you have D10, you can imagine that the orbital 3D now is have lower energy level than the 4s. So we will not violate anything in terms of energy rule. You still obtain the optimal energy level for the whole system. The reason is more you fill electron in the orbital D, lower energy level of orbital D will be. So when you fill half or when you fill all the orbital D, then the energy level of 3D is lower than 4s. So it's justify the fact that you have 3D5 or 3D10 before satisfy the 4s2. So it also means when you have the orbital D with less than electron or empty electron, like 0 or 2 or 3 or 4, for sure, the level of orbital D still higher compared with 4s. Okay? So to be short, this arrangement of the energy level is correct first for the atom, which is neutral. When you talk about the cation or anion, it will be different. Okay, that means you remove one electron or you add one electron to make anion, it will be different. We talk about the neutral atom first. The second, this order is correct when the number of orbital field in the orbital, number of electron field in the orbital is not high. More you fill electron, the energy level start low down, and at one moment, the order of the orbital 4s 3D, for example, can be inverse. Is it clear? Is it clear?
So, Professor, I do have a question.
Yep, please.
So, from what I have heard from you, that the lower the energy level, well, or rather, the atom would prefer a lower energy level, right?
Yes.
Okay, then I understood. Thank you.
Yes, because you see, when you stand at the 8th floor, you have a higher potential energy, and it risks to be pulled down. But if you go to the 1st floor, then it will not fall down anymore, right? So all the natural system, you can look any system in the nature, they could prefer to have lowest energy level. I'm talking about the potential energy, lowest potential energy level. So they will be more stable. When you want to make it unstable, so become more active, so you need to bring it at a higher energy level. That is the very general rule. So the key word in all the chemical process is energy. So the chemical compound in the normal state, in the ground state, in the most stable state, it would prefer to have lowest energy level. Okay? And when you excite it, you bring it to the higher energy level, it will find a way to relax back, to come back to the more stable one. Okay? Now, we can do a little bit practice. So, what could be the electron configuration of silicium, A or B?
A. I think
A,
it's A.
right? So, this should be this one. And what could be the electron configuration of the borons?
It's also A.
Also,
A. Okay. What will happen if one atom inside the silicon crystal is replaced by one atom of boron crystal? So here you have neon 3s2, 3p2, and here you have helium 2s2, 2p1. Okay. So imagine that you have a silicium crystal like silicium here, and you have other silicium like this. Okay, so X silicium here, this one, will be surrounded by 1, 2, 3, 4 atoms around. Okay, what could happen if you pick out this one silicium atom and you replace this one by one boron atom? You get what I mean? What could happen? For the whole silicium crystal. Anyone can comment?
So I think there will be a lack of electrons because the outer cell like the outer cells of boron is lack of had less electrons than the outer cell of silicon. So there seems to be a lack of electrons, I think.
So yes, thank you, Vu. So let's say if you take silicium here and you put the boron inside, we can say now it's like this. So boron here. Okay, because the borons have only 3 electrons. Why the silicium you have 4 electrons in the outermost layer. So you take out 4 and you give back 3. So it means that there 1 electron deficit. They are like 1 electron. And when it's like 1 electron, it can represent by 1 positive charge. We can say like this. Okay. So it looks like here you have a positive charge in the system. Is it correct? Now, what could be the electron configuration of the nitrogen? So you know that the nitrogen is 7. So what could be the electron configuration? So you will have the same helium, and you have 2s, 2, 2p3. Okay? No. Oxygen, carbon, borons. Oh, hold on. Yes. Okay. So you have helium, 2s2, and 2b3. So now, if you replace one silicon by one, you replace silicon by nitrogen. So what will happen?
Can you repeat your question?
Now, so when you repeat one silicon by borons, you will have a deficit. You like 1 electron in the system, right?
Yes.
So the situation now, if you replace one silicon by one nitrogen, what could happen?
Nitrogen. I think if nitrogen is also be lack of electrons because no, I think maybe it can be like have exists electrons because the outer cells of nitrogen, they have 5 electrons.
Okay, thank you. So yeah, it's exactly. So when you pick out this silicon, okay, and you replace by nitrogen. So now you have nitrogen here. Because nitrogen has 5 electrons, while for the silicon you have only 4, and you have 5 here. You take out 4 and you put back 5. So that means you have 1 negative charge here. You have 1 excess electron. And you have lack of electron. Okay? So imagine that now you put 1/2 silicium, which have nitrogen replacing silicium, and another silicium where you have boron replacing silicium. So that means you have one side where you have a negative charge and one side you have positive charge. What would happen? When you put together, the charge from the negative side will fall to the positive side, right? That is the electricity, that electrical cost you learn. So that means it will have electron movement from the nitrogen silicium to the boron silicium. So exactly, it will create the electrical current. So this is the fundamental operation of the silicon solar cell. Okay, so you see, by very simple understanding of the electron configuration of the silicon, of the carbon, of silicon, of the nitrogen and borons, you can understand how fundamental point of view of silicon solar cell work. That's my main message. Okay. Any concern? Any question? Is it understandable?
Yes, Professor.
Okay, thank you. Now we move on. So you see that in the silicon technology, you have a silicon here. Okay, you can make the replacements of the silicon by borons. You can make also doping or replacement of the silicon by nitrogen or phosphorus to make the solar panel of silicon. So nowadays in Vietnam, you have quite a lot of factory where the silicon solar cell is produced, especially in Bắc Giang province. You have quite a lot of factory, and if I remember well, 2 years ago, Vietnam was the second producer of silicon solar cell over the world, the second best producer. But at the same time, we are not using very much of silicon solar cell inside Vietnam, but we silicon solar cell to overseas, specifically to Europe and US. So now we talk about the periodic table. So you can see that at the time of Mendeleev, he create the periodic table of elements based on the periodicity of the chemical property. That means when you start from one element, you see the chemical property change, and at one moment given, the chemical property be back to the same pattern. That means you start from the lithium, which is the very active, we react violently with the oxygen. When you move to the barium, the activity low down. When you go to the carbon, the activity of the reaction with oxygen low down. And when you move to the noble gas, there's no more activity, there's no more reaction with oxygen. And then you'll be back to the same column where you talk about the sodium. The sodium produce exactly the same chemical property to lithium. It reacts violently with oxygen with water. And then when you move forward, you move to the magnesium, the activity low down, and so on. The barium, the low down, and so on. So they put the element based on the periodicity of the chemical property. That means how the chemical property develop and repeat. And how can we explain this periodicity of the chemical property. So the reason is because of repetition of the similar electronic configuration. So you can see here. So you take from hydrogen, you have only one electron, 1s. The lithium, the same property to hydrogen, you have 2s. The sodium, same to lithium, you have 3s. Potassium, 4s. Rubium, 5s, and so on. So that means that the element have a similar chemical property because they have similar electron configuration. When you talk about the outermost layer, so outermost layer of hydrogen is 1s, outermost layer electron of the lithium is 2s, sodium is 3s, potassium 4s. So basically, they are different in the energy, they are different in the size of orbital, but they have the same character in terms of spin and in terms of shape of the orbital. Okay, so the behavior of chemical behavior of the element similar because they have comparable electron configuration. So for the same column 2A, barium, magnesium, calcium, strontium, you see that they have the same electron configuration. And when you talk about the noble gas, all the outer layer of the element are filled with electron. That means you have 2 electrons occupy the 2s, 6 electrons occupy 3 orbital B of the 2p. So there no single electron. So the chemical activity is very low. Okay. That we talk about one column. So how about the rows of element? So when you start from the lithium and you move from the left side to the right side, you see that lithium have they have the same electron configuration, but there are difference in adding. When you move from one atom to another one, you add up one more electron. So you move from the orbital 2a to orbital 2p, okay, and eventually to 3a, 3b, and 3d. So because you change, you keep the more or less the same size of atom, but you change, you move from the orbital s to the orbital p. That means you change from the shape and the size of orbital. So basically, you expect the different chemical behavior. So by the definition, the atom have the outermost layer contain only the electron s. We call the block s element. So we call the element s. That means the outermost layer has only orbital s. If the outermost layer has orbital s and orbital b, so we call the block b. So the p orbital p element. If the element have orbital s, b, and d, then we call the A element is d element. Okay, the d element belong to the class of element we call the transition element, transition metal. Okay, so if you take the general block, general periodic table of element, you will see that you have the block S here, you have block B, and in the middle you have the block D. That means the transition metal. Okay. Now, please pay attention on the column 6B here. And if you take the molybdenum, you have this orbital, the electron configuration. Okay. And of course, this one, you can draw like this 45, 5s1. Okay. And you take the tungsten. The tungsten electron configuration is this one. you can draw also like, you know, 4F14, 5D4, and 6F2. Okay. So if you keep the 4F orbital, you look at the outermost layer. You see that for the molybdenum is 4D5, 5S1. And in the case of tungsten, they draw 5D4, 6S2. At the same time, you have in the same column, the two elements, they are in the same column of 6B. How can we explain this? Basically, when you have the same column, that means you have the same electron configuration. Is it correct? Okay. And in the group of 6B, we call the two elements have 6 electron D. And at the same time, in the orbital, in the periodic table of elements, they draw by this one. So anyone can explain why this kind of confusion? Why they confuse in the writing the electron configuration and putting in the same column, even they have a different electron configuration. Am I clear in my question? To explain my question?
Could you repeat the question, please?
Okay. You learned before that, let's say, when you look in the column, right? They are in the column because I mentioned they have comparable electron configuration. You have a 1s, S1, 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 S1 here, right? So it's a when the atom in the same column, that means they have a same electron configuration, S1, S2, something. So here you have S2. However, if you take a look in the column 6B, you see that on molybdenum and tungsten, they are in the same column. Okay? So you expect that the two atoms have the same electron configuration. However, when you look in the way they rise the electron configuration, like this one, you see that there are different. The molybdenum is expressed by S1D5, and the tungsten expressed by S2D4. So they are different, but they are still in the same column. So it's a confusion. So my question is, how can you explain this kind of confusion? So am I clear now in my in expressing my question?
Yes, you're clear.
Okay. So how can we explain this phenomena?
Well, I think this confusion can be expressed because maybe molybdenum and wolfram, they have similar chemical properties. I think so.
Yes. So basically, in reality, the molybdenum and tungsten behave comparable in a similar manner in terms of chemical activity. They are comparable. For example, in the nature, you find the molybdenum and when you don't have a molybdenum in the environment, to build up the enzyme. The biosystem, the living system, can replace the molybdenum by tungsten and reproduce the tungsten containing enzyme with exactly identical property. So in terms of chemical property, the molybdenum and tungsten are comparable. So that's why that explains they are in the same column. And also, when you talk about the D element, the fact that you put the orbital S, orbital D are not very obvious all the time that orbital S will be at a lower energy than orbital D. As I mentioned, more you put electron in the orbital D, the energy level will go down. So you will have a system where the orbital D inverts the orbital S, have a lower energy level. So it's spin first, right? So it's kind of depend on the atom to atom. Comparing the orbital S and the orbital D is not all the time exact. For S, S will be lower than D or invert D lower than S. Okay. So it's gonna keep the profile. Okay. Now we move to the practice. Let's work on the first question. The electron configuration of the iron 26 is which one? A, B, or C?
I think it's B.
Okay. Correct. So you apply the diagram you have here. The electron configuration of iron 2 plus gas iron is which one? A, B, or C? Now you remove the electron.
I think it's C.
C? Why C?
So basically, you remove 2 electron, but then because the atom would prefer a lower energy state, you must use 1 electron from the S to transfer to the D suborbital for, I guess, balancing.
Thank you. Any other comment? All agree with the option C?
I think the answer is A.
Why A?
I think A is because the layer 4S is laying outer of 3D. So when the electrons is taken, they must take from the outer cells.
Yes, exactly. So even 4S have lower energy, but it's in the outer layer. You get what I mean? So you start from the nuclei. You have 1 layer n equal to 1. You have 2. You have 3. So here you have 3D here, DPS here, and then you have 4S, 4 layer n equal to 4, where you have a SPD as well. Okay, so you have 2 electron for S2 here. Okay, even it's lower energy in terms of energy, you can expect that here is energy. You have 4S2, and you have 3D here. Okay, but because it's outermost layer, so it's easier to be removed. Okay, so the take-home message you need to take and remember is for the 3D orbital. So for the transition element, when you remove electron, so when D block element form ion, the 4s electron are lost first. This is take home message because they are the electron in the 4s is outermost layer. Okay. So the correct answer here is A. So the same question, what could be the electron configuration of the ion 3 plus?
So that should be A, right?
Yes. So it should be this one. Okay. So here a few messages. First, when the block element form ions, so to remove electron, the 4s electron are lost first before you lost the d electron. And this diagram is applicable only for the neutral atom in their ground state. And when you fin 3d orbital, the fin 3d orbital will have a lower energy, so it will be lower than 4s. So at one moment you can inverse the order of 4s 3d. Okay, that's the three main messages we can learn from the exercise. Next, to practically bit. First question, what is electron configuration of the cobalt? Can you comment?
I think C.
I think it's B.
Hmm? Which one?
I think it's B. For the first question, right?
Yes. So, correct answer here is
I think it's A.
B. So, what could be the next answer? The electron configuration of the cobalt 2 plus is
That should be A. A.
so that should be A, right?
Yes.
And what could be the third question? The electron configuration for the cobalt 3 plus?
It's A again.
Okay, good. Yeah. So you see now you can perform very well on the question. There will be no problem for that. Now, a little bit more chemistry. So here is experimental result. Observation. If I take the cobalt nitrate powder, dry one, without any water vapor, this compound has no color, colorless powder. I pick up this powder, I dissolve it in water, I'm going to observe the pink solution. Okay, then to this pink solution, I add Na3 inside. The color change from pink solution to become brown or blue color. My question is, oh, sorry, how can we explain this phenomena? By what we learned today and the day before, the last week lecture, Dr. Đức Anh explained to you. How can we explain this phenomena? You get what I mean? Is it clear, my question?
Yes, it's clear.
Okay, so try to go on this.
Professor, can I answer?
Yes, please.
So since I joined in late for the lecture, I didn't really know what happened before. But from what I know, the change of like this phenomenon can mostly be explained by the fact that each molecule has their specific, let's say, specific properties that that if they react with each other, they could create a new molecule that have other properties that could, for example, be of different color or absorb specific colors, which would make them appear, for example, like in this example, pink or blue. And for the first reaction, which is dry CONO3 with H2O, even if the first molecule is colorless, when it reacts with H2O, it creates a new molecule which might have a different properties that will make it absorb every color in the color spectrum except for pink, and so it will show the color pink.
Okay.
And the same can be said for the other reaction.
So basically, the key point is following. Here you have a cobalt 2 plus, right? Okay. Here also you have color cobalt 2 plus. Here you have also cobalt 2 plus. Huh? And we say that the color we see is due to the absorption of the compound, right? And the absorption of the compound is due to the electron transition from the ground state to excitation state when it's absorbed the photon. So here, the point is, you have the cobalt 2 plus everywhere. On 3 compound, you have cobalt 2 plus. Does that mean the electron configuration of the cobalt will be identical? So how, with the same cobalt 2 plus, with the identical electron configuration, the electron transition could be different, so the color will be different? That's my main question. You get what I mean? Yep.
Could I try, Professor?
Yeah, please.
So the degenerate d orbital of cobalt, I think it can split into different energy level. And so when we include H2O into this new compound, it will shift the equilibrium of the energy gap, and that's why the energy gap changes. And so it can turn from pink into blue solution because the energy gap expand, or basically it's changed, and so it the electron of the lower energy level orbital, suborbital, sorry, could absorb a different wavelength of the line.
Thank you, Hùng. But how? Yeah, exactly. So the key point here is how the orbital d of the cobalt will be split, right? It will degenerate the orbital d. So if you have the orbital d split in different energy levels, so you can have an electron transition from the lower energy level to higher energy level. That's the general thing you comment. My next question, can you elaborate? Can you develop a little bit more? Why for the cobalt powder, cobalt nitrate powder, which is colorless, it has no color? Why it have no absorption? Can you comment why? Because if you have a d orbital difference, we should expect that it have a different color, but it's have color. You get what I mean?
So maybe it's not currently in its lattice form.
Mm-hmm. Thank you, and thank you, Hung. Very nice. Who can comment more on this question?
This is related to like the hybridization, because which the ligand is water and amino cobalt 2 plus express the different kind of hybridization. So they have different in electron configuration, and so the electron transition also different, so it makes the different color.
Okay, so Wu, you mentioned that they will have a different electron configuration, right?
Yes, I think so.
But basically, I agree with Hung, the one who commented before. The electron configuration will be similar. They are all cobalt 2 plus. Anyone can comment, please? Hmm?
I'm sorry, I don't know.
Anyone? Yeah, thank you. Anyone can try to think. Let's we think a little bit about that, and we try to discuss this question.
Maybe just because it's one is simply in solid form and the other is in form. I don't know.
Okay. Let's we think a little bit. Let's say 2-3 more minutes, and then I move on.
Teacher, can I try?
Yeah, please.
So I think it is cobalt when it have electronic from oxygen. Cobalt will have a higher energy, so the color is appears with can I say in Vietnamese? It's more easy.
Yes. Okay.
Có nghĩa là khi mà cái oxy nó cho cái electron orbital trống của cobalt thì có nghĩa cobalt sẽ có mức năng lượng cao hơn, thì có nghĩa là cái ánh sáng của cobalt nó sẽ mạnh hơn ấy, thì nó sẽ có màu sắc hơn là khi mà cobalt có mức năng lượng thấp hơn. Và NH3 thì cái electronic ở trên cái nitơ nó sẽ có mức năng lượng cao hơn là ở trên electronic, tại vì electronic ở trên nitơ nó kiểu hoạt động hơn, tại vì cái nitơ nó ít bị lực hút hạt nhân nó yếu hơn của oxy, thế nên nó sẽ thay thế nước, thì NH3 sẽ tạo liên kết với cái cobalt dễ dàng hơn. Còn màu sắc thì như ở bên trên.
Okay, thank you. Your friends, your classmates say that basically in the case of cobalt aqueous compound, that means with water, there's a bonding between the cobalt and oxygen. So the electron from the oxygen will contribute to make this bonding with the cobalt. And when you move to the ammonia and Na3, so the nitrogens have a stronger reactivity compared with oxygen. So it will replace, so Na3 will replace water. So it produce the complex, the compound with the same cobalt in the center, but surrounded by the Na3 compound. The color change because the interaction of Na3 to the cobalt will be different compared with the interaction of the oxygen and cobalt. But it still remains the question, why the cobalt nitrate dry one, the dry one without water, without Na3, have no color. Okay. So okay, the time is running out, so I propose that we go a little bit faster. Now, before we talk about this observation, may I propose question by question following? Why can we see the color of one compound or one solution? What is the origin of the color that we see of one compound of one solution? You get my question? First,
Yes.
we need to understand why we see the color.
Well, I
What
could
be
explain.
Yeah.
Well, I said before, it's because the molecules, because of their chemical properties, they absorb a specific length of color in the color gamut,
yes.
and then they only refract one color or multiple.
Thank you. Yes. That's correction. It's not a chemical property. That's a physical property, the absorption. Okay.
Yes. Sorry.
Now, I explain first why we see the color. Here you have the famous one, and maybe you may want to remember this. We call the color wheel. In the color wheel. Okay. So what does it mean? So this color will tell you that if one compound absorbs in this area, violet, you will see the color. Our eyes will see the color is compensated with the color of the absorption. That means we will see the color of yellow in the opposite. It also say if the compound absorbs the yellow light, you will see the violet color. If it absorbs the violet light, you will see yellow color. If the compound absorbs the photon in the red range, you will see the green color. And if it's absorbed in the green range, you will see the red color. If absorbed in the orange, you will see the blue. And inverse, if it's absorbed in the blue, you will see the orange. So here, the number here representing for the wavelength of absorption. So it means if it absorbs, the compound absorbed in the wavelength of the 430 to 480, it's absorbed in the blue, then you will see the orange color. Okay. Is it clear? Now, is it clear for you guys?
Yes, Professor, but can you mute everyone? One student forgot to mute himself.
I don't have the capability to mute because I'm not the host. The host is
okay.
the general education department. That's crazy, but like that. Okay. So try, please to mute this. Okay. Now, let's relook at the absorption spectrum of the cobalt. So here you have the cobalt water 6+. So you see that it absorbs in the wavelength of 500 nanometer. So 500 nanometer is somewhere here. Okay, so it means that you will see the color between the orange and red. So that's why in the solution you see the pink color. Okay, you will see the pink color because it's absorbed like this. Now, when you have the cobalt ammonia compound, then it absorbs a 650 nanometer. So let's see, 650 nanometer could be somewhere here. Okay, so you will see the color in the range of blue one somewhere here. Okay, but because of this compound, it absorbs 2. So you will have a mixture of the green and the brown color. So you can see the blue color, or sometimes you see the brown color. Is it clear, my explanation for the moment?
Yes, it is.
Okay, so here we pretend, we remain at the step to understand that why we see the color and why different absorption of the compound will provide different color that we observe. Now, the second question, why the cobalt 2 plus, when it is surrounded by water, and the cobalt complex, the cobalt 2 plus, when it's surrounded by ammonia compound, will have a different absorption, right? That's the second question we need to solve. Now we move on that. Vũ Tuấn Long Giang, can you mute your mic? So, okay, let's be back to show why the cobalt 2 plus in the only 3 compound, but they absorb different wavelength, and because they absorb different wavelength, so you see different color. And we learned from the previous slide that the cobalt 2 plus should have electron configuration of D7. And you know that you have 5 orbital D. Okay, you have a D, X, Y, D, Z power, D, X, Y, D, Y, Z, and D, X, Z. Okay, do you remember that? You have a 5 orbital. So let's say we are talking about energy. So we put the energy diagram. First, all of the 5 orbital will have the same energy. So we have 1, 2, 3, 4, 5. You have a D7, 1, 2, 3, 4, 5, 6, 7. Okay, because they are at the same energy level. So in the dry compound, the electron cannot absorb photon to move anywhere because they are all at the same level. So that explains the cobalt cannot absorb the sunlight. If it's not absorb the sunlight, you cannot see any color. Is it clear?
Yes.
Yes. Now, you put the water surround. So what you can understand? You imagine that you have this coordination, Z, Y, X. Okay? So you put your cobalt here. You have a 6 molecule water. It's going to arrange like this. Water, 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 O2, water, water, and water here. Okay? So we have a 6 molecule water surround here like this. Okay. Is it okay? So you can imagine that here you have the red one is oxygen atom, and surround you have a water like this one. You can have oxygen. And in the oxygen, you have orbital p, like this, which have electron. Okay, as Wu mentioned, that oxygen have an electron. Now, you look at the 5 orbital you have here. So the first one is arranged like this one. So you will see that you have the d orbital and the p orbital of oxygen is in the direct interaction. They are very close each other. So here in this situation, you have dx orbital interaction with the pz py of oxygen. Okay, and both have electron, so the interaction is very strong. Okay, the same thing if you take this orbital. So this orbital like this, right? So you have here the direct interaction. Here you have direct interaction dz⁻². Interaction with the p oxygen is very strong interaction, and here you have strong interaction. Okay, so how about the orbital dxy? You know that the dxy is in between xy like this. Okay, so you can see that the interaction between the oxygen here and the orbital here is quite far. The distance is very far. So here you have weak interaction between the dxy and the p oxygen. Do you understand? You have a 2 orbital with the electron density. They are negative in charge. Closer they are, stronger interaction they are. Further distant they are, weaker interaction they are. Is it clear?
Okay.
More or less, yes.
Yes. So let's say now, from the 5d orbital, they are the same level if surround they're nothing. But now you put in the water, you will have 2 category, 2 group of the orbital d. One group contain x⁻², y⁻², and dz⁻², which have strong interaction. So that means strong interaction, that means at a higher energy level. So you will have 2 orbitals dx, y, and dz⁻² at a higher energy level than the normal orbital d. And you have a 3 orbital dxy, dyz, dxz. They are at a lower energy level because the interactions are weaker. So you see that you start from the same energy level and now you split into 2 energy levels. So you take the same 7 electrons, you will feel like this. You 6 already and you have 1 here. Okay, so here you have a gap of energy different than 0. So now if you send the photon with the energy equal to the gap of energy here, then the electron from here will excite to this position. So you have the color, you have the abstraction spectrum, so you have a color. Now is it clear for you guys why you put water inside? You have the color. You have the color. Is it clear?
Yes.
Okay.
Yeah.
So now you put ammonia to replace water, what will happen? Like Wu mentioned, the interaction, or someone mentioned, the interaction of ammonia with the cobalt is stronger than the interaction of ammonia of the water with the cobalt, with the same cobalt. So you keep the same here, you replace the ammonia. So you still have the same splitting. However, because of the difference splitting, stronger splitting. So you will have now dxy, dyz, dxz, and then you have now the splitting dx and dz power 2 with a larger e. So that means the splitting e with Na3 will larger than e with the water. Okay, so you see that they will absorb different photons. Okay, is it clear?
More or less, yes.
Because they absorb different photons, so they will have a different color. Okay, so that this something is interesting and important when we put together the understanding of the electron configuration, sorry, and the energy splitting related to the color of the compound, the stability of the compound, and so on. Okay, so this is the first exam, very classical one. You can see in a lot of textbook, and in the lots of general chemistry class. Okay, so I invite you guys to look at this in more detail, and then we will, if you have any question, we will discuss later. Okay. So so I mentioned here already. So this is something. Okay. Another phenomena you can learn also thanks to this understanding of electron configuration. You see that when you have the same iron compound, you have one compound like this with the color of the, let's say, red, white color. But when you heat up, it's become orange color. And when you cool down, it be back to the red, white color. And when you look at the oxidation state of irons, you understand the oxidation state does not change. It's still iron 2+. Okay. So you may want to ask what could be the phenomena behind of this observation. So basically, you still have the compound with a set of 5d orbital. Okay. So when you have electron splitting at the lower temperature, so you have 6 electrons in the ground state. But so in total here, you see that here the total spin equal to 0, here total spin equal to 0, here equal to 0. So LS mean low spin because the total spin equal to 0. Okay. And then when you heat up or you apply pressure or you send the sunlight to the electron from the ground state will excite like this one. Okay, so you can imagine that 2 electrons from this here will excite up to the higher energy level. So now you can see that you have a total spin equal to 0, but here 1, 2, 3, 4, the total spin is 4 times 1/2 equal to 2. So that's why we call Hs equal to high spin. Okay, and when the electron excites to the high spin state, the gap of energy here reduce. So you have gap 2 smaller than gap 1 here. So you change the color. Okay, so sometimes when you take a compound, you heat it up, you see the color change. You think that's it because of chemical reaction? No, the compound is still the same. Only you change the spin state from the low spin state to the high spin state. And when you cool down, it will be back. Okay, so imagine that if you define the low spin is state 0 and high spin is state 1. So you have 2 states. 0, 1, 0, 1. So exactly the way the computer science guy used to store information by using two states 0, 1. So you can imagine that you can design a chemical compound with different spin states to remember to store the data. So that's in the field of imaging field we call the spin crossover for the moment. So you see, you understand the electronic configuration. If that write out that like what you learn in the high school is quite easy. You need to remember some rule, but it's quite easy. But apply using the understanding to apply to some specific case to understand all the phenomena that you observe, then to what you are working to make progress in terms of chemistry, in terms of data storage, and so on, is more interesting and more useful. So I hope that by showing the kind of exam, you will feel more useful of all the classes you are studying, and with that, you will study better with more motivation. I hope so. Okay.
Okay.
So, do you have any question? I could end my class here. It's time up already. So, any question?
Professor, will you put the slides on Moodle, because I missed half of the class today because I woke up late?
Yes, yes. Okay.
Okay,
So
okay.
I will put the slide in the Moodle. Okay.
Okay, thank you.
If no more questions, so thank you for attention, and we see next week. Okay. See you next
Bye,
week.
Professor. See you next
Bye,
week.
Professor.
Bye.
Bye bye.
Bye, Professor.
Professor.
Bye, Professor.